My background was those days, early days, was in modelling and atmospheric dynamics. I then got it sort of involved in weather forecasting, as the name suggested, from modelling. That sort of took me into observations for forecasting, and finally, towards the end of my career, this has evolved into observations and data product requirements for climate. And it's in that context I'll be speaking today on behalf of GCOS. Now, I'm a meteorologist, not a metrologist, and I only sort of really know one person in the audience, so I thought I'd better give you a little bit of an introduction to GCOS. It's in some ways a small effort, in some ways it's a very large effort, because what we call the Global Observing System for Climate, or the GCOS, it really encompasses the climate components of a large number of observing systems. We have the WMO observing systems, and Martin spoke about GOR, in particular the Global Atmospheric Watch, but we also have the Global Ocean Observing System, terrestrial observing systems, led under other bodies. WMO, we've heard about International Oceanographic, Intergovernmental Oceanographic Commission, Food and Agricultural Organization, and then we have observation elements of research programs and other systems, some initiatives under the group of Earth observations, all contributing observations related to climate. And we together envisage this sort of system of systems as a global climate observing system. And that lives, in fact, inside a larger system of systems under the group of on Earth observations. And our program assesses and communicates overall requirements for the system as a whole, advises on implementation and reporting, and reviews and promotes progress. And we're concerned not only with the observations themselves, but also how the data are transmitted, managed, glued together from different instruments to produce long data records, and formed into products, perhaps by integrating information from, or data from, different observing systems. We're sort of small at the sort of official level. We have a program director and a staff of only 4 or 5 people based at WMO. We have a steering committee, of which I'm the chair. We have co-sponsored panels and their working groups, and I'd like to thank NPL for allowing one of their members, Tom Gardner, who I think's here somewhere in the audience, but yeah, hello Tom, to serve on one of our most active working groups for atmospheric reference observations. Also work through other programs like the World Climate Research Programme. But there's a much more substantial effort, of course, behind it. There's the national, normally I'd call them National Met Services, but I thought I'd better call them National Weather Services, and other national and regional agencies that actually make the observations and trying to make them following certain principles and guidelines that we have suggested as GCOS, and also to the standards that are come from WMO and the like. But they also provide monitoring centres, analysis centres, lead centres for various activities. They support regional development, and they coordinate specific national activities. And then, because we're a system of systems, the secretariats of the individual observing systems, related technical commissions, space agency coordinating bodies such as GCOS, Committee on Earth Observation Satellites, various expert groups, etc., all sort of work together to make this whole thing function. Requirements. No, it's not coming up on the screen here. I do have to look at the screen to see the words. I can't read them here. We cyclically assess progress, assess adequacy, and assess requirements. In fact, we're about to start off on a new cycle right now. This has primarily been in support of the UN Framework Convention on Climate Change, but I think requirements and needs are changing, and we're going to have to address further some of the requirements for climate services and under the UNFCCC adaptation to climate change, rather than just determining how the climate is changing and work on towards mitigation. Oh, sorry. Requirements are for observations, But not only observations, the data records and the products, and these have been set out in various documents. And this is actually where the essential climate variables came from that Martin mentioned in his last talk, that they originated from GCOS in one of these documents. They provide indicative requirements. As we've heard, long-term stability is a specific important need for climate observation. And that's something that's not formally yet embedded in WMO requirements, for example. They have requirements for targets for what they call accuracy, or they probably call it uncertainty these days, but they don't have requirements for stability yet. And as Martin also mentioned, we don't quite speak the same language. We try and be GUM aware in our documents, but it's not fully applicable to some of the data products we deal with, and it's not a language that sits particularly well with some of our user groups either. So the language is a little bit tricky. Process, we tend to prepare these things through editors, steering committee panels, workshops, with all drafts subject to open review, but of course these people, we still have to decide what to do with the review comments, of course. But we do present the results to the parties to the United Nations Framework Convention for a consensus response. And our whole process is, I would say, largely transparent and traceable, but it could be improved. Okay, just a few examples now. Surface observations. We heard in the opening remarks that actually the global mean surface temperature is one of the better characterized climate variables. I mean, we do have a very dense coverage of surface stations. It was something like 36,000 observations coming in every 6 hours for weather forecasting purposes. A subset of these stations will be operated in principle to a rather higher standard or produce rather more careful monthly means, and it's those monthly means on which the global temperature trend graphs were presented. We saw 3 sources, but one can also do the same calculation just using quantity, not quality, using all the observations, and we do that through weather forecasting type models, and we get pretty well the same result, which is reassuring. So, I mean, things can always be improved, but it's not in bad shape. We do need to ensure that observation continues at least to set a baseline locations, and there are some clearly worrying gaps in the system. And continuing observation needs to be supplemented by doing the best we can with past data, sort of getting them into modern formats, either from paper or from well-meaning attempts using technology that's no longer applicable. Converting data into modern digital formats and getting them into modern databases within nations, but then increasing the international exchange of these data, getting the data to the international centers, and then using data assimilation, modeling techniques, blending in, assimilating the observations into model runs, and some form of downscaling to fill the remaining gaps. And these gaps aren't only in network coverage, they can be a gap in the fact that what we call a surface observations in meteorology normally means 2 meters for temperature and humidity, and perhaps 10 meters on a mast for wind. And that's where this bulk of observations is taken. But of course, if you want to site a wind turbine these days, one actually needs the wind conditions up to at least the top of the turbine blade. And last year, this slide said 150 meters. Now, from a press release about something, I increased it to 180 meters. And we just don't only have these observations at a few places where balloons are launched. So we really do need modeling to try and fill the gaps and provide the sort of information needed for siting, for operating wind turbines, for example. And in all countries, there's a scope for data rescue of some form or other. And then we heard of the problem of the upper air temperature in the previous talk. We saw this graph of which I think was largely based on balloon data at selected sites across the world. But the mainstay, another mainstay of this, and probably the predominant source of information these days, does come from the satellite system. We've had these now 33, 34 years in considerable numbers. And this is a picture of the timeline from 1979 to 2012 of what's been flying that's providing sort of information on temperature and humidity through the depth of the atmosphere. These satellites measure things over relatively broad layers. These layers are rather broad, but there's just lots of overlap in this modern instrument here. But each of these is an instrument type, microwave sounding unit to an advanced microwave sounding unit. And each of these bars is a particular satellite, and sometimes the data sometimes it goes off and they process it again when another one dies. I mean, the satellite could have been working there, but they didn't have the ground processing to deal with it then. So we have this sort of record of satellite data over 40 years from various instruments, all measuring something slightly different, but has to be blended together. But don't worry about the details, but this is just two particular levels in the atmosphere in the lower stratosphere, sort of 20, roughly a layers around about 20 to 30 kilometers high, or nearer 20 than 30. This is a sort of layer centered around about 5 kilometers or so in the mid-troposphere. And each of these lines represents the adjustment we have to make to the data from each individual satellite and each individual instrument to actually sort of produce a sensible product when we reprocess this record. And one can see that perhaps the main thing is that there's no absolute calibration of any of these instruments. You launch a new satellite and the average temperature comes in up to 2-3 degrees different from an earlier one in the sequence. These biases tend to be relatively stable. These are more or less horizontal, but not quite. This is a satellite whose orbit drifted, and so the sun heated the black body calibration target, so it wasn't as constant as it was intended, and so all these wiggles sort of come in there. And we have to adapt for these changes over the course of time in the satellite data, but we also have to adapt to the fact that there are changes going in other components of the observing system, and our models can drift as well as a consequence. So, there's a real hodgepodge of adjustments needed to be made to these satellite data. So, as I said, the requirements for observations, data records, and products, and for the generation of the data records and products, so we develop guidelines, we work with partners to implement the guidelines and broader practices for developing data sets and reporting on how the data sets are built through data inventories that carry a lot of metadata. This is really sort of work in progress. Also supporting efforts on the assessment into comparison of products, and here efforts such as we'll be talking about later through the GCOS, what's it called, Quality Assurance for Earth Observation Group. This is where interaction comes in, interaction more explicitly with another GCOS working group, its working group on climate. So I think this is probably something we'll be discussing more in the groups. And for observations, we have the concept of a network hierarchy involving comprehensive baseline and reference networks. So that the comprehensive network is basically anything that's giving us something reasonably respectable and usable on climate. The baseline network, well, it'll have lower spatial density, but hopefully, I use the word standards. That's probably a bit high. Maybe it's driven by the quality of the operating practice. Perhaps might have been a better thing to say there. But then we have a sort of baseline network which is run rather better, and then just a few small high-quality reference sites, where for the upper atmosphere we have all networks and satellite systems. We have a baseline subset of balloon measurements, which we call the baseline network, of 180 of those. Probably there are one or two newer satellite systems that are stable enough to add to that at some point. But then we have a set of reference sites providing very high quality radiosonde operation and supplementary measurement profiles. This is where Tom Gardner comes in on the working group that's looking after how that's run. And then ideally we would like satellite reference missions as well, but it's a little bit difficult to sell at present. And then and you've seen this before now, I thought I'd put in some words about what we do with carbon dioxide and methane in particular, because here, as we heard in the previous slide, there's a very direct link with meteorological activity. So some of this terminology has popped up before. So this WMO GORE network, the Global Atmospheric Watch Network, is the designated baseline network for carbon dioxide and methane. The NOAA lab in Boulder at ESRL is one of the world calibration centers. Another one is the Japan Meteorological Agency. They handle CO2 and CH4 respectively. And NOAA operates the central calibration laboratory for both species. And its role there includes maintaining this mole fraction scale, which we've heard about for the species, a few other species here. Comparisons with the independent primary scales, traceability to SI, which is where this community really comes in, and ensuring transparency, complete and prompt disclosure of problems, uncertainties, etc. And then we have the comprehensive networks, which involves other in situ measurements, remote sensing from the circa, aircraft-based measurements, which may be research aircraft or instrumented commercial aircraft, instrumented Lufthansa flights, and satellite-based remote sensing. And I just put one. So the idea is to improve our estimates of emissions from what we call a top-down approach, using observations of what's happening in the atmosphere, either bulk measurements from satellites or the more accurate, but more local measurements from FLAST data. This is NOAA, Esrael, and cooperating institutes, to produce more refined estimates of the emissions, which of course we need to check back against independent measurements and estimates, and over large areas we need to check, well, this is not CO2, but for CO2 we would want to sort of check over, we probably can't do this over a national scale, but we can do it over regional scales, or we will be able to soon, to check that all the emission estimates make sense, or emission reporting makes sense. Okay, just to move on very quickly now. Of course, I've talked more about the atmosphere, which is sort of where my own background is, but we have ocean observations to be concerned about. Considerable observations in recent years from drifting buoys, although the numbers are dropping off a little bit. We also have moored buoys shown in this graph, and moored buoys are the blue ones, the red ones. Then we have these Argo floats that go up and bob up and down in the top 2,000 meters of the ocean, and when they surface, they broadcast their observations. This is a network that's been established really in the last decade, and it's sort of transformed our ability to work out, to sort of get the energy balance of the atmosphere right, because a fair bit of the energy isn't going into heating the surface, it's going down into the ocean and perhaps into the deeper ocean, and developing a strategy for that is a priority. I'm not sure quite where we are with reference measurements here for the ocean, but probably some of these moored buoys would be making what we would call close to reference quality observations. And there are also sort of ship cruises doing networks of cruises doing very detailed in situ measurement, which would provide a baseline, if not a reference. Terrestrial observations, I put this one in because it shows that we're not just interested in long-term climate change, we're interested in short-term prediction on a season and above. And for that, of course, one needs to monitor what's going on with the state of the surface. Just knowing what's happening now can often give you a predictive capability for the humanitarian impact down the line. If your wet season has failed or whatever, if you're inheriting already dry soil, you can be sure there's going to be a problem happening. And this is the East African drought of a couple of years ago, and various indicators that we can produce to show what's going on and inform an early warning system for famine, for example. And the last slide, just to say there's plenty else that one really needs to worry about where there is progress, but still a need to enhance observation or data exchange. anything to do with the water balance, which is actually water availability in a warmer climate is a real concern. We worry about dust for health reasons, but also, it affects solar power generation. Deposits of dust on panels inhibits their activity, but the actual dust will also block the solar radiation in the first place. Wildfires for their emissions into the atmosphere, carbon emissions, but also emissions of pollutants that affect air quality as well as public safety. Forest conditions, including the sort of undergrowth that can feed the fire, including soil carbon, is critical. And also marine conditions, particularly in coastal zones, carbon tied up in mangroves, coral reefs, etc. And so that's going to be a very big area where standards are going to be needed if one's going to enter any of these proposed systems where developed countries pay developing countries for maintaining their forests and marine ecosystems. So there's probably something where some rather strict standards of measurement are going to be needed if money's going to be changing hands. Then, of course, more than half the population of the world is now living in urban conditions, and we tend to make our meteorological measurements in nice fields with trees and well-trimmed hedges around the site, etc., and it's not quite like that where many people live. So we need sort of notions of temperature, humidity, air quality actually in the cities themselves. And of course there are other trace species, the greenhouse gases. So that's it. That's a sort of picture of what we do, some of our concerns, some of the opportunities for metrology. I didn't put any real concluding slides up, although I think I would really echo the concluding remarks made by the previous speaker. And clearly there's a big role for metrology in here, but we do also have to have a balance. We don't want only reference quality observations because we need the spatial coverage. We need to do the day-to-day job, the forecasting out to days, seasons, perhaps a bit further ahead. And we need comprehensive global coverage to validate models, to generate the data for models. So we need a balance. We need this hierarchy of networks. Thank you very much.